All right, thanks. All right, so first I'm going to start off this talk with a game that you're going to play with me. And the game is the following. Okay, so I imagine that you're holding a basket of fruit that's initially empty. And at each time step, what I can do is I can either insert one fruit into the basket, or I can look in the basket and take one fruit out. Okay, and you can see the items as I put them in and take them out, but you're not allowed to look inside the basket to remind yourself of what's in there. You have to sort of just keep things in memory as you're monitoring this sequence of insertions and removals from the basket. And using bounded memory like your brain, okay, when I say query, you have to tell me just one fruit that's still in the basket. There might be 1,000 fruits in the basket, but you just have to tell me one. Okay, does it make sense? Okay, so we're gonna play the game for a second. Okay, so. Okay, good. Okay. So I inserted a strawberry, a watermelon, a grape, an orange, a peach, a banana, another peach. So now there are 2 peaches, but then I removed one, so there's only 1 peach left. And then a mango, but then I removed the second peach, so now there are no peaches. And I insert a bunch of fruits into this basket, and you're watching me put these fruits into the basket. And at some point I'm going to start deleting a lot of fruits. Yeah, it's pretty rough. So now I'm removing fruits. Okay. Yeah. You got to keep up with the stream, Query. Okay, great. So I'll take a few guesses. Strawberry, no. Watermelon, no. I mean, those were inserted, but they're just not there anymore. No. Mango. Nope. I heard pear, mango, no, coconut. If each person in the room just remembered like one random fruit that showed up, like one of you would have gotten one of them, right? I mean, but actually there's 1 plum left and 1 lime left. So, I can share the slides with you if you want to verify, but I promise you. Okay, so this problem, I'll call it the SupportFind problem. And, this is some jargon that I'm going to define in the very next slide. But basically the problem is this, okay? So there's a vector z, which is like a histogram. It's indexed by fruits, right? And when I insert a fruit, I increment that coordinate. And when I delete a fruit, when I remove a fruit, I delete that coordinate. And at some point when I say query, just tell me anything in the support of this histogram, okay? Anything that's non-zero. So this Turnstile streaming model, okay, so in general, there's a vector z, it's my histogram, and it supports coordinate-wise updates, like zi gets zi plus delta. In this case, delta was always 1 or minus 1 for inserting or removing a fruit. And I want a data structure that supports various types of queries to z. And I want this data structure to use a little memory, like the memory in your brains, for example, right? You can't remember every single thing that you saw. And there are a few different sub-cases that people focus on in the literature here with turnstile streaming. One is insertion only. That just means that you're always inserting, you never delete. Okay? So for example, n is the size of a dictionary. So n is the dimensionality of this vector, the number of fruits that exist in the universe, types of fruits that exist in the universe. So here n is the size, say, of a dictionary, and there's a Google search for word I. So now you increase the frequency of word I, right? And someone wants to know what are the frequent words people have been searching for in Google over the last hour. So that's also some kind of query about z. So that's insertion only. There's the strict turnstile model within turnstile streaming. That's where you're allowed to have positive and negative updates, but you're not allowed to ever have negative frequencies. Okay, so for example, in the fruit game, right? I can't delete a fruit that's not already in the basket. Okay, and another place where that shows up is big graphs, right? So imagine that the dimensionality of z is on a graph of capital N vertices. The dimensionality of z is capital N choose 2. Those are all the edges that could possibly exist in the graph. And then people are inserting and deleting edges, like 2 people just became friends on Facebook, so now there's a new edge. And then later, they started dating and they broke up, and one unfriended the other, right? So now they unfriended, and now the edge is deleted. Okay, so you can't delete, but you can't unfriend someone if they were never your friend in the first place. And then there's the general turnstile model, where deltas can just be arbitrary. You can insert, you can delete, things can go negative, right? And there, you can imagine, again, going back to like the Google example, there are all the searches from today and all the searches from yesterday, and I want to know which words had big differences in their frequencies between today and yesterday, because maybe some event happened that caused, I don't know, election results to become all of a sudden popular, right? So you can imagine everything from today would be a +1 update, everything from yesterday would be a +1, everything from today would be -1. Then zi would be like the difference in the frequency between today and yesterday, right? So you can use these different subcases to model different kinds of problems. That's turnstile streaming in a slide. Yeah, question?
I have a question. When you gave the insertion-only example, you said something like the search is done in the last hour. So there is a second parameter.
Oh, right. Yeah, good. Yeah. So then, yeah, you would have to basically create kind of one of these data structures on the hour, let's say, and then you just use that one for the hour. But you're right. Yeah, there is something called the sliding window model, which has this time parameter. But let me not get into that. Okay. So this SupportFind fruit game. So fruit game was the SupportFind problem, right? Give me anything in the support of Z. Of course, in the insertion-only model, that's really easy. You just remember like the first thing you ever saw. But it's harder when you have deletions. So this thing has been very useful as kind of a basic subroutine for lots of problems. I'll say some more about that in a second. But I think that kind of one of the first paper really to show just how powerful it is for dynamic graph problems, it was this paper by Ongu and McGregor 7 years ago. And they looked at the following problem. Suppose I have a graph on n vertices, or on v vertices, and the Facebook problem. People are inserting edges and deleting edges, and then I want to query like, are these two vertices connected? Is there a path between them? Or even, more information, give me all the connected components of the graph. Or even more than that, give me a spanning forest of the graph. Okay. So they actually gave an algorithm for this dynamic spanning forest problem using the fruit game data structure as a subroutine, and their algorithm used v log cubed v bits of memory. Okay. Notice that for this problem, like it's not even obvious. I mean, it's not even obvious if you're maintaining a graph in a stream. If someone says, give me any edge that's still in the graph, just one edge, right? I mean, that's the fruit game problem, and it's not really a priori obvious how to solve that, right? If people are only inserting edges, it's easy, but if someone can insert and delete edges, how can you return any edge at all? Maybe the edges you're storing got deleted, right? And several other works studied not only this fruit game SupportFind problem, but samplers. So don't just return an arbitrary index in the support of Z, but rather return an index with probability proportional to the weight of the frequency of item I. For example, proportional to the frequency, or the frequency squared, or whatever. Okay. So the state-of-the-art solutions for this problem, first of all, are randomized. They're Monte Carlo randomized, which means when someone says query, I'll actually say a correct fruit with probability 1 minus delta. But with probability delta, I'll say something completely bogus. Okay? And I won't know necessarily when I failed. So the state-of-the-art results use this amount of memory, log 1 over delta times log squared n bits, and succeed with probability 1 minus delta. And recently it was shown that for weighting functions where like the weight of the probability, like let's say you actually want a sampler, where the probability that you output item I is proportional to zi to the pth power, then for any p between 0 and 2, it turns out you can do this in the same space. Okay, and that's something recent by Jaira and Woodruff. Okay. So since this 7-year-old paper by Ongu and McGregor for dynamic spanning forest, and they actually solved other problems as well, there have been a number of graph problems, dynamic graph problems, that have used either SupportFind, the fruit game, as a subroutine, or the sampler version as a subroutine, right? And you can imagine, just from that example I gave, you can imagine why this is a useful subroutine to have, right? Like if you want to output triangles in a graph, or dynamic or spanning forests, or matchings, or whatever, like the very first basic thing you have to be able to do is just tell me any edge that's actually still in the graph. Okay, so good. So yeah, I listed a bunch. So K connected components, minimum spanning tree, spanners, et cetera, vertex cover. There are lots of things you can do with this as a subroutine. Okay, some of them needed this pth power kind of sampling property. But okay, so so the question is, what's the truth? So there's this log 1 over delta log squared n bit upper bound by Jauhari, Soglum, and Tardosh. And what I showed with these collaborators is that finding any element of support Z in turnstile streams, even in strict turnstile streams where things don't necessarily go negative, requires this amount of space. Okay, so in bits. So I mean, obviously there's always the deterministic solution, which is you remember the entire histogram, right? So that's like n words of space. So you're never going to show a lower bound bigger than n. That's why there's like a min n there. But what this lower bound says is essentially up until that threshold, when you get n, the correct lower bound is log 1 over delta times log squared n. And it kind of gracefully turns into n as delta gets exponentially small in n. So this really is most of the time log squared n, right? And the lower bounds come from a reduction from a communication problem called universal relation. And I know probably, just a show of hands, how many of you are computer scientists? How many of you are not computer scientists? So it should be everyone else. Okay, good. So sometimes people just don't raise their hand, and then you don't know, like, are they not computer scientists, or maybe they're not raising their hand. So good. So I'll explain what I mean by communication complexity and universal relation and all that stuff. But basically, what we show is a tight. We give a tight characterization of the complexity of this universal relation problem in communication complexity. And I should also mention, once you've proved that this kind of subroutine is optimal, that doesn't necessarily imply that the downstream applications were solved optimally, right? Maybe there's a better way to solve dynamic spanning forest that doesn't use this as a subroutine. It uses something better. But what we showed, this is me and my postdoc watching you, is that we can actually prove that this v log cubed v, at least for dynamic spanning forest, is an optimal bound. You cannot beat that. Okay. Yeah? Yeah, yeah. Oh, okay, sorry. So this apple, okay, so this whole fruit thing was one example of like a z you might care about, where n is the dimensionality of z. So in that example, n is like the total number of fruits that exist in the world. And then there's the graph example. In the graph example, n would be like v choose 2, right? So yeah, first of all, I just want to kind of separate these. The graph, there's no vertex with the fruit game. Like there's with graph problems that can be captured by this kind of model. The fruit game can be captured by this model, but the fruit game and the graph thing is not the same thing. Yeah, but I mean so these algorithms also can handle multi-edges. Our lower bounds, though, like if you could ask the question, if I actually wanted to store the frequency vector, if the max frequency is at most r, I could write it down in log r bits. So the kind of the trivial upper bound is n times log r bits, whereas these lower bounds don't have any dependence on the max frequency r. Yeah, so our lower bounds don't,
in the dynamic graph
yeah.
setting, can I change the number of vertices as well if I want to?
Oh, can I add vertices later? Let me think for a second.
Never mind, you should continue.
Yeah, I have to think about that. Yeah. Okay, good. So first, in this one slide, I'll try to explain the upper bound. And I guess, a lot of the talks here are like compressed sensing, Fourier matrices. Okay, this is an FFT, I guess. So yeah, this slide will show you why compressed sensing sparse recovery is relevant for this problem. But then once I'm done showing you the upper bound, the lower bound is like communication complexity, which is a lot of like information theory. So let me tell you how the upper bound is, which is actually due to these 3 people over here. So let D be a data structure solving the k-sparse recovery problem. What is that problem? That problem says if I'm lucky and the support size of z is the frequency vector, is at most k, like if I have at most k fruits in the basket, then I should return the frequency vector. Okay, so let D solve that problem. And hopefully many compressed sensing folks have seen, know what I'm talking about when I say this, but I'll just in case not, I'll have something here to say how to do that. And then what I'll do is I'll pick a random function which maps my universe of all fruits into a range of size log n, 1, 2, 3 up to log n, such that the probability that a fruit gets mapped to j is 1 over 2 to the j. Okay, so you can say, well, I need to have a low memory solution. How can I store this random function that takes a lot of random numbers? That's not low memory. It turns out that you don't really need a truly random function. You just need a pseudo-random function, and I don't want to get into that, but you can do it. Okay, so here's the data structure. Here's the overall data structure. So you're going to take a bunch of k-sparse recovery data structures, d1, d2 up to d log n. They're all deterministic, meaning they always work. As long as support z is at most k, they work. Okay. You're going to set k, which is your kind of support size bound, to some constant, 100 times log 1 over delta. And then whenever you see an item I in the stream, a fruit, okay, you hash I with this random function h, that will send it to a random level. Mostly they'll get sent up here, because half of them get sent here, a quarter gets sent here, etc. So most of the time it'll be in the upper part. But you send it to a random level, and that data structure will be responsible for processing it. Okay? So why is that a sensible thing to do? It's because the following algorithm will work now. Okay? So mind you, nothing in the problem statement of the fruit game said that the basket has few fruits in it. The basket could have a cajillion fruits in it. You still have to tell me one. Okay? But the point is, even if the basket had all n fruits in it, if you look at this level of hashing, how many people do you expect to hash there with the random function? A 1 over n fraction, right? So that's at most 1. And it's probably closer to 0 unless you have all the n fruits in the basket. So down here, you expect it to be empty, 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 empty. And then all of a sudden, when you get to the right level is basically 2 to the j, the true support size over 2 to the j is roughly k. Then it won't be empty. So then when you ask this data structure, recover the vector, it'll give you a fruit. Okay? So that's how it works. And what's the total space? The total space is log n times the space for each one of these. And the space for this, I won't justify. It's k log n bits, where k is the support size you can support, and k is log 1 over delta. So k log n is log 1 over delta log n times another log n is log 1 over delta log squared n. So that's where the space countdown is coming from. And how do you actually implement this k-sparse recovery data structure? You do what I guess some people call syndrome decoding. People a couple hundred years before that called it Prony's method. Okay, and the idea is, look, what I'm going to store in memory is a linear sketch. Like instead of storing z, I'll store pi z in memory. Okay, and based on pi z, I want to be able to recover z if I'm promised that z is k-sparse. Okay, when can I recover it uniquely? It's when this linear map is an injection on the k-sparse vectors. So I want that for all k-sparse x not equal to x prime, pi x is not equal to pi x prime, which means that x minus x prime is not in the kernel of pi. But x minus x prime is a 2k sparse vector. So what I want is I want a matrix, right, such that if I take any m by 2k columns, it has full column rank. And this matrix has that. Okay, some Vandermonde matrix. And there's a fast algorithm to recover it, which is either called Prony's method or syndrome decoding, depending on the community of the people you're talking to. Okay, so this is the connection, I guess, to compressed sensing. Yeah.
Usually, Vandermonde or Prony's method, once noise is included,
Yeah.
it becomes pretty.
Right. So yeah, this is sort of perverse. There's no noise because this is not really even a compressed sensing problem, right? We're just using a tool that was developed for compressed sensing to solve this like graph data structure problem. And also, this is not even over complex numbers. This is over like a finite field. Because if I assume that I'm always inserting or deleting things, and let's say that I'm promised that frequencies never get bigger than r, right? I just need to work over a finite field of size at least r or something. Yeah, so yeah, you're right. I mean, if I were actually doing compressed sensing, then I wouldn't want to use this. But I'm not really doing compressed sensing. I'm just borrowing something compressed sensing people use and importing it to do something else. Any other questions? Okay, so that's their algorithm, Johari-Sargun-Tardosh algorithm. And how do you now prove that something like that is optimal? So this is the lower bound, which is what me and my friends proved. And first, before I can prove the lower bound, I need to do a detour into communication complexity, because maybe not more than half of the people said they're not computer scientists and might not be familiar with these, this thingy. So what's communication complexity? So remember, I wrote down at some point that we proved that the R delta arrow pub of universal relation is something. What is this? What does this mean? Okay, so here's what it means. The pub means there's a public random string in the sky that everyone can see. Okay, there it is. F is some function which maps x's and y's. F of xy is some z. There's some function. Everybody knows the function as well. And then there are two players. Okay, there's Alice and Bob. Alice gets some little x in this set. Bob gets some little y in that set. And ultimately what they want to do is they want to compute f of xy. Okay? And the arrow there means Alice sends a single message, an L-bit message to Bob, right? And Bob, based on that message, has to compute f of xy. And the delta means that it can be a randomized protocol, right? Where Alice and Bob can look at that public random string in the sky to decide what they're going to do. Like Alice can use it to decide, based on her input, or his input, okay? Based on his input and the random string in the sky, decide what message to send Bob. And Bob will look at that message, will look at his input y, and will look at the random string, and then decide what he thinks f is. But he has to succeed with probability at least 1 minus delta. So what does that r delta arrow pub f mean? It means over all protocols, communication protocols, meaning like how Alice behaves, how Bob behaves, to solve this problem that have success probability at least 1 minus delta, what is the minimum message length that allows Alice and Bob to solve this problem? Okay? What's the minimum L that's achievable? Okay. So so the f that's relevant for us is an f called universal relation, and it arose really out of computer science in this earlier work of Karchmer and Wigderson on depth lower bounds for circuits. I think I will probably skip the history just because I'm time crunched, and more than half of you are not computer scientists, so you might not care. Okay, so let me skip this. But the point is, there's a connection between this universal relation business and proving depth lower bounds for circuits in computational complexity. Okay, in circuit complexity. So what does that mean? Okay, it doesn't matter. It doesn't matter for today. But here's what universal relation is. Universal relation is Alice gets a binary string of length n, Bob gets a binary string of length n, and they're promised that x and y are not equal to each other. Since they're not equal, in particular there's a bit where they're not equal, and what Bob has to do is find any such bit. Okay? And the deterministic communication complexity of this problem is very well understood. People have protocols and lower bounds that are tight up to 3 bits of communication, okay, an add of 3 bits. Deterministic means there's no delta, it always succeeds. Okay? So what we do is we show a tight lower bound on the up to a constant factor on the one-way communication complexity where you actually are randomized and you're allowed to fail with some probability delta. Okay? And actually, binary strings are basically the same thing as subsets of 1 to n, right? So Alice gets a set, Bob gets a set. They're promised the sets are different. Find something that's in one but not the other. So we actually prove our lower bound even for the potentially easier special case where we're promised that Bob's set is a subset of Alice's set. So even if Bob knows that his set is a subset of Alice's set, but a strict subset, even that's hard. Okay, so this is our theorem that kind of this communication complexity lower bound holds. Okay, good. So what does this have to do with the fruit game and SupportFind? So let me explain that, because if I don't get to actually prove the main theorem, I at least want to convey how everything fits together. So I claim that the space complexity of finding an element in this Turnstile model in support Z with failure probability delta is at least the minimum communication cost required to solve universal relation in this model that I described. And why is that? I will show that if you had a really good solution to the fruit game problem, you could use it in a black box way to solve this communication problem. Okay. How do you do that? So A is a solution to fruit game. Okay, so what's going to happen? Alice is going to look at her input set, right? Her input set is a binary string, which is a set. It's an indicator of a set. And for every index I that's in her set, she's going to insert that fruit in the basket. Okay? So there's this algorithm, A, it's a black box. Everything that's in her set, she's going to feed it into the black box and saying, I'm inserting all of these into the fruit basket. Okay? And then now she's going to say, black box, tell me your memory contents. Okay? Now she gets the memory contents of this algorithm, and she sends those memory contents as a message to Bob. So now, since Bob has the memory contents of the algorithm, he can basically continue running the algorithm from where it left off. And then for everything in his set, he'll say, remove that fruit. And then now he'll ask the algorithm, the fruit basket algorithm, query. And it's going to tell him a fruit in the basket, okay, with probably 1 minus delta. So in other words, it has solved the, it's the same problem. It has solved the universal relation problem. Okay, so that was not too bad. Okay, so the message length is exactly the space usage of A, and we know that the message length is at least the minimum message length. I mean, that's the definition of R delta pub. So the space has to be at least that communication lower bound. Okay, so how does one prove this lower bound? I only have like 4 minutes, right, 11:15. So how does one prove such a thing? So the lower bound plan is, again, some kind of reduction. And ultimately, it's going to be the pigeonhole principle, okay? So we're going to violate the pigeonhole principle if you had too good a solution for universal relation. So suppose you had a really efficient communication protocol P for universal relation. I'll use it to design an encoding scheme for size m subsets of 1 up to n. Okay, and how many of there are there? They're roughly n over m to the m, right? N choose m, up to some, is roughly this. So the log, so any encoding scheme which maps, size m subsets into like bit strings, well, L had better be at least log of n choose m, which is roughly m times log of n over m. Okay? So the question is, how can I design such an encoding scheme, right? I'm going to use this communication protocol as a black box to design a Las Vegas encoding scheme, or a randomized encoding scheme. That usually works. Or Las Vegas means it always works, but let's ignore that. Okay, good. So notation, in my last 3 minutes, let's say E is the encoder, D is the decoder. Alice is the first player in this protocol P that is this black box protocol you gave me, and Bob is the second player. And S is a subset of size m that's to be encoded. Okay? So how does the encoding and decoding work? The encoding of S will simply be call Alice on the input, which is the indicator of S. Okay? And now the decoder gets that message, right? The decoder gets the encoding, but the encoding is just this message. How does the decoder decode? Well, he's just going to peel off elements one by one. So he's going to build up his set T. Okay, so T is going to eventually be S, hopefully. Start off as the empty set. And then I know that I have to find m elements. S is an m element set. And what I'm going to do is call Bob on the input where Bob has, T as his set, right? So what's in S minus T? Well, anything in S, because T is the empty set right now. Okay? And then I go through the for loop again, and then whatever I recover, I put into T. I go through the for loop again. Okay, now I know that 5 is in the set. What's in the set S, which is not 5? And then I get a new element, and I just keep calling it, iteratively until I peel off everything after m iterations, and then now I return it, okay, and I'm done. Okay, so that's all. Sounds very simple, but it's a little bit bogus. Okay, and the reason it's bogus is what I want the decoder to be able to recover from the encoding with like good probability, with probability 90% or something. Let's try to understand what's the probability that the decoder fails, because remember that this whole protocol is a randomized protocol. Well, every time we call Bob in the protocol, he fails with probability delta. I do it m times, so by union bound, isn't my failure probability delta times m? So as long as I choose delta to be less than 1 over 2m, I succeed with like half probability, right? Do people get what I'm saying? Or have I? Okay. Do people get what I'm saying enough to realize that this is completely bogus? Okay. Yeah. So what I can do is I can set m to be roughly n, and what this says is, I could encode any size n over 2 subset using this protocol. Therefore, I have a lower bound. How many size n over 2 subsets are there? An exponential number. So log of that would be linear in n. Therefore, I have a linear in n lower bound for this problem. Okay, so I'm done. So I'll just cut out this slide. That's bogus. And the reason that's bogus is I have an upper bound of log 1 over delta times log squared n. So in particular, I could actually solve this in log cubed n space. or lock-you-down communication. So what went wrong in this argument, and what went wrong is adaptivity. When you talk about a Monte Carlo algorithm or a Monte Carlo communication protocol or whatever, the assumption is that the adversary who gives you the inputs is not allowed to see your randomness, right? But if you think about how this decoding scheme works, the first query is okay, but the second query to Bob is on an input that depended on the output of the first query, and therefore is correlated with the randomness of the protocol. That's not allowed. And okay, so now I'm basically out of time, but the whole art is then doing something more sophisticated that gets all around this whole dependency issue, okay? So that's all I have, I guess, time for.